All right, moving into our last example for lesson 3.3. We're looking at the distance problem, which I always think is like the classic meme on the internet about why people don't like math. We've got like some moving objects and we want to find the distance between them. So in this question, we've got ship A, ship B, and port C, very original names. Ship A is 10 kilometers due east. So for these questions, sometimes we have to remember our direction. So I always say never eat shredded wheat. I'm not sure how you remember it. So you kind of want to have that in the back of your mind. So ship A is due east of Port C. So Port C is here and ship A is over here to the east. But it's sailing in towards the port. And then ship B is sailing away from Port C and it's heading to the north. So I've got Port C down here. I'm going to draw a picture for this. Remember, whenever I'm trying to make sense of a problem, it always helps to draw a picture. And ship A is somewhere off to the east of this. I'm going to draw it nice and big so we can. And then we've got ship B, and ship B right now is at the port, but it's going to sail away. It's going to head up to the north. So right now, the point C is actually the same as where the ship B is. Now, because ship A and ship B are both moving, I'm going to say that this is their starting position. I'm going to call it A1 and B1. And then I'm going to also put their position after some amount of time. So after some amount of time, ship B is going to be due north of port C. So there it is. I'm heading up towards it. And then ship A is going to be heading towards port C. And it's like, if you want to be accurate, it is moving a little bit faster than ship B. So this distance here should be like a little bit bigger, but that's just details. It's not actually going to affect the math of the problem. But what I want to know is the distance between these two ships as they're moving. So I want to know this distance here. So I've got a couple of variables here that I've introduced. I'm going to write some let statements. Initial. I don't know what's going on with my tablet. And so these second positions are going to be based on some amount of time passing. So I'm going to define that time so I'll put it down here. So after time t, and then you have to tell me how you're measuring time. So in this question here, the speeds were given in per hour, so I'm going to measure time in hours. Sometimes the question will ask you about how many minutes or how many seconds, but I would go with the initial unit that you were given and then convert the time at the end. It's going to be easier for you. So then the next thing I've got here, I've added to my diagram. So I've defined three kind of sets of variables: initial positions, secondary positions, the time in hours, but there's also this variable d. All right, so we need to find a way to come up with an equation, right? Because remember, I want to know in this question, how close will the two ships pass? So what I'm looking for is how close do they ever get? I'm looking to minimize that distance between them. And so if I'm minimizing the distance between them, then I need to come up with an equation that says like d equals some stuff, right? That's what I'm looking for. So I need a way to measure this line here. And what I know in this question is originally this distance here is 10 kilometers. And I know that if I wanted to find this distance here, ship A is moving at a rate of 5 kilometers per hour. So that means if I wanted to find the distance, I could just do 5 times however many hours have passed, right? Remember, t is the number of hours. So if 2 hours have passed, then I would do 5 times 2 to tell me how far they've gone. And then over here, B1 is equal to C. There's no initial distance. But he's moving at a speed of 4 kilometers per hour north. So again, if I wanted to figure out this distance here, I would do 4 times the amount of hours that have passed. So I've got some stuff now labeled in my picture. In order to come up with an equation for this line here, though, what I notice is this kind of looks like a right triangle here. So I'm going to go back to our favorite old Pythagorean theorem. And the Pythagorean theorem tells me I can just add the sum of the squares, I can find the sum of the squares of the 2 legs of the triangle. So I wish I knew an expression here for this side length, but I know that this whole distance is 10, and this distance over here is 5t, so the leftover bit here must be 10 minus 5t. So now I've got 2 expressions. I'm going to combine them using the Pythagorean theorem. So my equation is going to be d squared, that's the hypotenuse, is equal to the one side length squared plus the other side length. And I'm just talking about the side length of this triangle here, right? So it's the 10 minus 5t. And then I can solve and make this an expression for the distance in terms of time by taking the squaring over and square rooting this expression. And I'm fine in your work. Once you practice this, you're going to get used to moving that square root over. So I'm okay if you skip this first line and just jump in right here at the square root. Okay, so we have our variables defined. We have our function in terms of one variable. We need our domain. And so again, the x variable here is the time, the t. So we need to come up with some expressions for the time. Now here in this story, we're starting with time equals 0. That's the smallest amount of time that can have gone by. So I'm thinking about finding the smallest, and here it's going to come from just that logical that we're not going to have negative time in the story. Now to find the largest, what I'm going to be thinking about is like, where should I stop measuring here? What makes sense? Well, the ship A is heading in here, and I'm not going to go past port C, like it's crashing into port C here. Even if it could, like say port C was actually down here and it could sail right by it, the distance here, this guy's heading up. So once this guy passes, once ship A passes port C, B is going to be getting further and further. So a logical conclusion here is to stop measuring when A gets to port C. So one of the 2 moving objects is going to get to the original position of the other moving object, and that's when I'm going to stop. So I need to figure out, well, what is the time? How much time does it take for ship A to get to port C? So remember that the speed, you might remember, like you might have the little triangle, right? That speed is always equal to the distance over the time, like kilometers per hour. And so if I want to solve for time, I bring the t up and the s down on the other side, and time is equal to the distance divided by the speed. And so here, the total distance that A is covering is 10 kilometers. And the speed that it's moving at is 5. And so it's going to take 2 hours. And you might have been able to tell that just from this story. They're nice and simple numbers. But sometimes you'll want to be able to find that comparison. So I'm okay in a simple story if you just tell me that you're finding when ship A gets to port C, and you tell me that it's t equals 2. So we've got our domain then. We know that time is between these 2 values. All right, so now we're heading into the main part of our algorithm. I'm going to take the derivative, I'm going to set it equal to 0 and solve for t. So up here, you might want to rewrite this before you take the derivative. Maybe you're going to, instead of having the square root, you're going to write it to the power of a half. And inside the brackets, you might want to expand and simplify a little bit here. So I'm squaring the 4, and I'm squaring the t. And then here I'm squaring the 2 brackets. So I'm going to get 10 times another, remember there's like another bracket that matches. So 10 times 10 is 100. And then I'm going to get 10 times negative 5t, but then also negative 5 times 10t, or sorry, negative 5t times 10, which will give me negative 50 minus another 50, so minus 100t. And then negative 5t times itself gives me 25t squared. And you don't have to expand, like you can take the derivative of this guy as it is. Here, you'll just have to use the chain rule on this guy. You'll bring the 2 down, leave the innards, and then take the derivative of the inside. And I think it's even easier to just leave it. But I've gone down this path here, so 30, 41. All right, so I've got this simplified function. I'm going to take the derivative. So I'm using the chain rule here. I brought the exponent down, subtracted 1 from the exponent, and now I'm going to take the derivative of the inside function. And now what I want to figure out is, where does this derivative equal 0? So to find that out, I'm going to simplify this a little bit by writing this guy here has a negative exponent, so he's going to go down to the denominator, and the 82t minus 100 stays up top. When I move it down to the denominator, I'm just changing the 1/2 exponent back to a root. All right, so I want to know when this fraction equals 0. Remember, whenever you have a fraction that equals 0, it's really just the numerator that you need to worry about. You can imagine taking that denominator and multiplying it on both sides to clear it. On this side, it would cancel, and over here, I'd get 0 times that denominator, which just equals 0. All right, so now we want to solve for t. I'm going to bring the 100 over and then divide out the 82. And that reduces to 50 over 41. And eventually I'm going to change that to a decimal because we're talking about time, but for now I'm going to leave it as a fraction. All right, so we've got our t value, we've got our 2 endpoint t values. Now I need to check the y values. And they're not as trivial this time as they usually are, because there is an initial distance here when I imagine the initial distance between the boats, right? When time is 0, there is an initial distance of 10, and that should check out with your formula here. If you put in t equals 0, this guy here is going to be 0, and then over here I'm going to get 10 minus 0, that's just 10. I'm going to square it and then square root it. So I'm going to get 10 again. And so my initial distance is 10. That's just a nice check for me to make sure that it matches my diagram as well as my equation. And then the next one I'm going to check is the other endpoint. So I am plugging this into the equation. And I'm just using the part where I did square the 4 here. Plugging in my t squared. And you can use the original version, that's fine, of the equation, or you could use a more simplified version as well, that's fine. Either way, you should get a distance of 8 when the ship gets to the port. And again, you can double check, like, does that make sense with the story? After 2 hours, ship A is at the port, so it's right here. And after 2 hours, ship B has gone 4 kilometers north twice, so that's 8. That makes sense. And then the last one that we need to check is that 50 over 41. And usually that's what's going to end up being the value that you're looking for. Missing it. There we go. All right, and when I type this in, because I am just looking for the maximum distance, and I know I'm going to round it anyways in my summary sentence, or sorry, I'm looking for the minimum distance, I'll just write this down rounded to one decimal place. So I get about 6.2 kilometers here. So again, we were looking for the closest that the ships get. That's going to be 6.2, and it's happening at this time. So I am going to change that guy to a decimal for my summary sentence. It's about 1.2. All right, enjoy the homework.